I am Bijal Kansara, Assistant Professor from Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today we start our new chapter, chapter number 3, Non-linear application of the op-amp. These are the flow of content, introduction, comparator, op-amp as a voltage comparator, then types of comparator are two types, non-inverting and inverting, then comparator characteristics, comparison of non-inverting and non-inverting type comparators, and last topic is zero crossing detectors. Introductions. Op-amp used in an open loop mode of operation operates as a comparator. A comparator will produce either a high output voltage equal to plus V saturation or a low output voltage equal to minus V saturation only. Hence, it cannot be used as an amplifier. Some of the important applications of the comparator are window comparator, schematic trigger, zero crossing detector, etc. In this chapter, we are going to discuss all these applications of the op-amp as a comparator. Now, what do you mean by non-linear applications? All the op-amp circuits discussed so far are designed to operate linearly. The linearity achieved by taking the following measures. The first one is by using a negative feedback to operate the op-amp in its linear region, and the second is by using a linear elements in the feedback network. Means these two measures are taken to create a linearity. Okay, the first one is a negative feedback is used, and the second one is a linear elements is used in a feedback network. But if we operate a high gain amplifier such as a op-amp with the positive feedback or with no feedback, it will operate in a saturation, means positive or negative side. This is called as a bistable behavior of the op-amp, and it is a highly non-linear. Means if we operate a high gain amplifier such as a op-amp with a positive feedback or with no feedback, means if we use a negative feedback, it creates a linearity, but if we use a positive feedback or no feedback, then it will operate in a saturation, positive saturation, either negative saturation, and this is called as a bistable behavior of the op-amp, and it is a highly non-linear. The voltage comparator and the schematic trigger circuit using op-amps operate on this principle. Okay. Another way of forcing a non-linear operation in by using the non-linear devices such as the diodes in the feedback network. Means non-linear element like a diode is used in a feedback path. Example of such a non-linear circuits are precision rectifier, peak detectors, sample and hold amplifier. One more group of non-linear circuit consists of the circuit like a logarithmic amplifier and analog multipliers, etc. The non-linear circuit discussed in these chapters are comparator, schematic triggers, precision rectifier and peak detector. Now we discussed our first non-linear circuit, which is comparator. Now what is a comparator? The definition of comparator is that it is a circuit that compares two voltage applied at its input and produce either a high means 1 or 0, high means 1 and low means 0 output to indicate which input voltage is larger. Means the comparator has the two inputs and the output, one output, and it produces either a high output or low output. High indicates 1 and low indicates 0. The symbol show the this circuit, this is a symbol of the comparator. Not that the symbol is the same as that of op-amp. Okay. Now basic function of the comparator. The basic function of the comparator is to compare the voltage applied at one of its input that is applied at its other input and to produce an output voltage which is either VOH or VOL. VO means V output high or V output low. Let the voltage applied at the non-inverting input be denoted by V1 and the applied at the inverting terminal is a V2. Here, applied voltage at the non-inverting terminal is a V1 and at the inverting terminal it is a V2. Then the output voltage is given by if V1 greater than V2 means this non-inverting terminal voltage is greater than V2, V1 greater than V2, then we get output VOH, output high, and if V1 is less than V2, then means the inverting terminal voltage is greater than non-inverting terminal, then we get the output is VOL, output low. Okay, this is the transfer characteristics. The voltage transfer characteristic of an ideal comparator is shown in this figure. It is a graph of differential voltage VD versus the output voltage V0. VD is a voltage difference between this input voltage. Okay, so in transfer characteristic we draw transfer graph of VD versus VO. Okay, the VTC means voltage transfer characteristic of the figure can be expressed mathematically as V0 is equal to V0H at VD greater than 0. For all VD greater than 0, output voltage is V0, and all VD less than 0, here VD is a positive, here VD is positive, here VD is negative. So we conclude that if VD is positive, then output voltage is V0H, and if VD is negative, then we get the voltage V0L. The voltage transfer characteristic is a highly non-linear curve at VD is equal to 0. At this point, VD is equal to 0. The output voltage is V0H or V0L. Means at one point we get the two different output. One is high and one is low, which indicate the voltage gain is infinite. The practical comparator can not have infinite gain. Hence, they can only approximate the ideal voltage transfer characteristic in this figure. The voltage gain of practical comparator are typically in the range of 10 raised to 3 to 10 to 10 raised to 6. For VD greater than 0 means positive, V1 greater than V2, the output voltage is constant at V0H, where for VD less than 0, we get a constant negative output voltage equal to V0L. It is important to note that V0H and V0L may or may not have an equal magnitude. Okay. Now, next topic is op-amp as a voltage comparator. When the speed is not a critical parameter, the op-amp can be used as a comparator. This is a main condition. When the speed is a not critical parameter, the op-amp can be used as a comparator. The op-amp used in an open loop mode of operation will operate as a comparator. A comparator in its simple form is nothing but an open loop op-amp with two inputs and one output. A comparator in its simple form is nothing but an open loop op-amp with two inputs and one output. It compares the signal voltage applied to one of the input of the op-amp with the known voltage called as a reference voltage applied to the other as an input. Here this is a reference voltage which is applied at the non-inverting term. Here This is the reference voltage and this is a applied voltage. Okay. The output of the comparator is either positive or a negative saturation, plus or minus V saturation, depending on which input is larger. Transfer characteristics shows the voltage transfer characteristic in this figure. This is the transfer characteristics of this comparator. Note that the voltage transfer characteristic is not as sharp as a VTC of the ideal comparator. In the previous slide we saw this voltage transfer characteristics of ideal comparator, but this is a transfer characteristic of a practical comparator. This is due to the finite slew rate of the op-amps. Higher the slew rate, the sharper the voltage transfer characteristic. Means slew rate increases, then the sharpness of this curve is also increases. When the input voltage is between the points A and B, input voltage between the points A and B, these 2 points, the relation between the input and output voltage is linear. Hence this region is called as a linear region. In these 2 points, suppose at 0 point to 8 point, as the V voltage input is increases, the output voltage is also increases in a linear method. For also negative voltage increase in negative region, the output voltage is also increases up to the point A and B. After point A and B, it becomes a constant value V plus V saturation, or in negative side it's minus V saturation. So region between the point A and B is called as a linear region. Now next is a types of comparator. Depending on which input terminal receives the signal input, the comparator are classified into 2 categories. They are non-inverting comparator and inverting comparator. Now we discussed the first type, non-inverting comparator. The schematic diagram of a non-inverting comparator is shown in this figure. The positive DC reference, here positive DC reference voltage is applied to the inverting terminal. Here positive DC terminal is applied to the inverting terminal, and AC sinusoidal signal is applied to the non-inverting terminal. Here plus is non-inverting and the minus is inverting. Okay, DC voltage is applied to the inverting terminal and the AC voltage is applied to the non-inverting terminal. As the AC signal is connected to the non-inverting terminal, this comparator is called as a non-inverting comparator. Okay, as the AC signal is connected to the non-inverting terminal, this comparator is called as a non-inverting comparator. Now operation and waveform of this non-inverting comparator. As the current through the resistor R1 is almost 0, here in this figure, the current through the resistance R1 here is almost 0, the voltage drop across this resistor is also 0. Hence the voltage V1 is equal to VIN and V2 is equal to V reference. Okay, V1 is equal to VIN and V2 is equal to V reference, because voltage drop across this resistor is 0. Okay, hence the differential input voltage VD can be written as, we know that VD can be written as VD is equal to V1 minus V2, but here value of V1 and V2 is VIN minus V reference, VIN minus V reference. Okay, when VIN is less than V reference, the inverting terminal is at the higher potential than the non-inverting terminal. Means where VIN this terminal is less potential than the V reference, then non-inverting terminal. Therefore, the differential input voltage Vd is a negative and the op-amp output will swing to the minus V saturation. In this figure, when Vin is less than V reference, Vin less than V reference, so the Vd becomes a negative because this is a lesser than V reference, so Vd is a negative. So the output of the op-amp will swing to the minus V saturation. And when Vin is greater than V reference, means when Vin is greater than V reference, then voltage Vd, this difference becomes a positive, so the output of the op-amp will swing to the positive. Okay, for this figure, this is the input voltage waveform, this is the input voltage waveform Vin, and this is a V reference line. Okay, now when at this point 0 to V reference, Vin is less than V reference. Okay, for this point 0 to V reference point, Vin less than V reference, so therefore Vd is negative, so V0 is minus V saturation, so V saturation is minus up to this point. Now at this point, after this point, Vin is greater than V reference. V reference is constant, but Vin is a AC quantity. Okay, at this point V reference is constant, but Vin increasing above the V reference, so Vd becomes a positive and the output voltage becomes the positive with saturation up to this point. After this point, Vin is also decreases value below the V reference, therefore Vin less than V reference, Vd is negative and V0 output voltage becomes a V saturation. So graph becomes like this up to this point. Okay, understand? If the reference voltage is made negative minus V reference and apply inverting terminal, then the input and output voltage waveforms are modified as shown in the figure. Means V reference is negative. If the V reference is a negative voltage, then the output voltage waveforms like this. Okay, this is the transfer characteristic of a non-inverting comparator. The transfer characteristic is a graph relating to the input voltage on x-axis and output voltage y-axis. The ideal transfer characteristic of a non-inverting comparator is shown figure A, and the practical transfer characteristic is shown figure B. It shows that the figure A shows that the output voltage is equal to minus V saturation for Vin less than V reference, and it switch to the plus V saturation as soon as Vin is slightly greater than V reference. The differential voltage need to the switch in the state of the output is ideally 0. Means in starting Vin is less than V reference, so at this time the output voltage is minus V saturation. After some points Vin is greater than V reference, therefore the output voltage is switched to the positive V saturation. The practical transfer characteristic says that the change in the output state take place when the differential voltage is about to 2 millivolt. Means it says that Vd value is about 2 milliwatt, then it changed from the negative to positive. The state changeover take place gradually, and there is a region of the uncertainty where we cannot exactly define the state of the output. Okay, in practical there is a slow, but in ideally it switch instantly. Now next is the inverting comparator. The schematic diagram of inverting comparator is shown in this figure. Note that reference voltage V reference has now been applied to the non-inverting terminal. Here at reference voltage is applied to the non-inverting terminal and the alternating voltage is applied to the inverting terminal. Okay. Operation and the waveform. The input-output waveform is shown in the figure number B. Assume that the op-amp to have a very high input resistance, hence the current flowing through the resistance R1 and R is very small. Hence the voltage drop across them is close, therefore we written as a V1 is equal to V reference. Here we can write as a V1 is equal to V reference and V2 is equal to VIN. Now differential voltage can be written as VD is equal to V1 minus V2 and put value of V1 minus V2 is equal to V reference minus VIN. Okay, when VIN is less than V reference, from figure, when VIN is less than V reference, the voltage at the non-inverting terminal is higher than the voltage at the inverting terminal. This makes the difference of voltage VD positive, hence the op-amp output will swing to the plus V saturation. And when the VIN is greater than to V reference, the voltage at the inverting terminal is greater than the voltage at the non-inverting terminal. Therefore, the voltage differential input voltage VD is negative and the op-amp output will be minus V saturation. The reference voltage is made negative, then the input output waveform is modified according to this figure. This is a transfer characteristic of an inverting comparator. When the VIN is less than V reference, the VD is positive, therefore the output voltage is plus V saturation, and the voltage VIN is greater than V reference, then the output voltage change to the V minus V saturation from plus V saturation. Practical transfer characteristics show that the change in the outputs take place when differential voltages range from 2 megawatt. The state change take place gradually and there is a region of uncertainty where we cannot directly define the output. Now, comparator characteristic. The most important characteristic of comparator are speed of operation, accuracy and compatibility of the output. First one is the speed of operation. The speed of operation must be high as possible. That means the comparator output should change its state quickly from plus V saturation and minus V saturation and vice versa. It must also respond instantly to any change in its input condition. Second is accuracy. Accuracy of the comparator is decided by its voltage gain, CMRR, common mode rejection ratio, input offset and thermal drifts. The high voltage gain will require a small differential voltage at the comparator input to change its state, and high CMRR helps the reject a common mode signal such as a noise. To reduce the effects of the input offset, the input offset voltage must be as low as possible. Third is compatibility of the output. The output voltage level of the comparator should be compatible to the CMOS family outputs levels. This is essential because the comparator is in many applications used along with the CMOS integrated circuits. Next is comparison of inverting and non-inverting type comparator. The first is input signal is applied to the non-inverting terminal of the op-amp, and for this is the input signal applied to the inverting terminal of the op-amp. Now second, for non-inverting, the reference voltage is applied to the inverting terminal and this reference voltage is applied to the non-inverting terminal. For non-inverting terminal comparator, output voltage is high for VIN greater than V reference and the output voltage is high for VIN less than V reference. Okay, and this is the transfer characteristic. Transfer characteristic non-inverting comparator start from minus V saturation and goes to the plus V saturation. Inverting comparator start with the plus V saturation and then minus V saturation. And limitation of the op-amp as a comparators are high operating frequency and the slew rate. Now, zero crossing detector. Zero crossing detector is shown in the figure. As you can see, zero crossing detector is nothing but a basic comparator circuit with a zero reference voltage applied to the non-inverting terminal. Zero reference voltage is given to the zero reference voltage is given to the non-inverting terminal. Means reference voltage value is 0 watt. Refer to the waveform shown in this figure. When the input sine wave crosses the zero, sine wave crosses the zero and becomes a positive at the instant zero. Okay, input positive at the zero. The differential input voltage Vd becomes a negative and the output voltage is swing to the minus V saturation. Means when Vin becomes a positive, the output voltage becomes a minus V saturation. When the sine wave again crosses the zero and becomes a negative instant t by 2, this is we take a period of 0 to t and this is a half period, so indicate by t by 2 half period. So after t by 2, at t by 2 period, the input voltage is again becomes 0 and that instant the output voltage swing from minus V saturation to plus V saturation, means becomes a positive V saturation. The zero crossing detector thus switches its output from one state to the other every time when the input voltage crosses the zero. You can see in this figure, when the input voltage changes its condition from the zero, when the input voltage touches the zero, the output voltage swing one state to another state. The zero crossing detector is also known as a sine wave to square wave converter, because at the input we given the sine wave but output we get the square wave. The application of this inverting zero crossing detector is two important application of zero crossing detector are phase meter and time marker generator. Now, non-inverting zero crossing detector. The zero crossing detector discussed in the previous slide is a inverting zero crossing detector. By slight modification in this circuit, we can obtain a non-inverting zero crossing detector. Okay. Note that inverting input terminal is connected to the ground. Inverting input terminal is connected to the ground. So V reference is a 0 watt and the input signal is applied to the non-inverting terminal at this terminal. Refer the waveform so that when the input triangular wave crosses the zero, this sinusoidal wave crosses the zero and becomes a positive at the instant t is equal to 0, means at this point if input voltage becomes a positive, the differential voltage Vd becomes a positive and the output voltage swing to the positive V saturation. At the t is by 2 time period, also input voltage crosses the 0 and becomes a negative, therefore differential voltage also becomes a negative and therefore output voltage switches from positive V saturation to the minus V saturation. The waveform are shown in this figure. The output voltage is plus V saturation for Vin greater than 0 and V0 is equal to minus V saturation for Vin less than 0. Comparator applications are in signal generation and transmission, automatic control and measurement, analog to digital converter, level detector, window comparator, voltage frequency converter and the switching regulator. Thank you.